Hey everybody, Dr. T is back. I am going to be talking to you about Chapter 9 today. I wanted to say thank you so much for filling out those weekly check-ins. I just really enjoy hearing from you, and since I can't see you, since we're quarantined forever, I hope not forever. It's just really a nice way to be in touch. So I think I'm going to be doing those weekly for the rest of the semester. That way it'll give you a little bit of a buffer points-wise, since I know lab has been challenging and just everything is challenging since we're far away. So that way you can let me know if anything's going on in your life that's affecting your schoolwork. Just be in touch a little bit. And yeah, so just as a reminder, there will be an exam covering Chapter 7 and Chapter 8 and the first half of this Chapter 9 material, so up through and including this lecture. It will be the exact same format as you had on the previous exam, so 10 multiple choice questions for which you'll have 30 minutes all morning on the day of the exam. And then the free response questions, which you'll have during our assigned class period. What I wanted to say was that last time I know students had issues submitting it on time, so I will build in some extra time to make sure that you not only have the class period to write and submit the exam, but also a little bit of extra time just so you can finish your thoughts, make sure you have enough time to upload the exam, and if you want, like a couple extra minutes to print it out, because I think that some people wanted to but were worried about timing. So that will be built in. And again, if you are trying to submit and the thing times out on you, I am here, so just let me know and I can always add an extra minute or two so you don't lose your submission. All right. So let's talk about Chapter 9. So in Chapter 9, what we're thinking about is, now that we know how electrons behave, now we know how atoms are arranged within, how electrons are arranged within an atom, now we're able to start putting atoms together and seeing how they go together based on how they share and exchange those valence electrons that they had, that we talked about in Chapter 7 and Chapter 8. And then once we put those electrons together, how the different bonds form between atoms and what kind of molecules we can form. So Chapter 7 was thinking about the electron, Chapter 8 was thinking about electrons within atoms, and now in Chapter 9 we're thinking about electrons within atoms forming molecules with each other. So let's start by talking about bonding and Lewis theory. So there are some ideas about bonding and why bonds form between elements. Okay, so we know that the main reason why we have bonding theories is to explain how bonds form. So we know that bonds form in atoms, and that's what makes molecules. So bonding theories are used to explain how atoms bond to form, that says form, molecules. Sorry, I know that just looks like FOM, so apologize for my penmanship here. So bonding theories, what's helpful about them is it allows us to predict which combinations of atoms are stable. So not just throwing atoms all together and being like, yeah, that'll be fine, but actually having some ideas about which atoms we should put together in order to have stable connections and stable molecules. And bonding theory, if it's effective, should also be able to help us predict the shapes of molecules, because knowing the shape of a molecule is what allows us to really think about, okay, well, how are these molecules going to act with each other? How are they going to react with other larger molecules like proteins, right? So this gives us a lot of information about physical and chemical properties of molecules. The one that we're going to be focused on for a pretty good chunk of this chapter is the Lewis model. So in the Lewis model, what we're going to do is we're going to think about every atom having its valence electrons be the active part. Okay, so we already talked about this in chapter 8, and we said the valence electrons do the work, and that's why we need to know how to count them. We need to know which ones are valence. And in the Lewis model, we use the valence electrons to think about bonding, and we represent the valence electrons as dots. So valence electrons are represented by dots. This model emphasizes valence electrons to explain bonding, which is why we spent so much time trying to understand that in chapter 8. And Lewis theory does some work in allowing us to predict properties of molecules. So stable molecules, so which ones would be stable, and their properties. So specifically what we're going to be thinking about is the size and polarity, which we'll talk about later in this chapter, of a molecule. All right, so let's talk about what kinds of bonds we can have and why bonds even form. Because I think what's sometimes confusing to people is like, okay, I understand that there are bonds in a molecule, but like, why are they even there? Well, there's a very good reason for it, and a lot of the reasoning actually comes from those properties that we've been talking about in chapter 8. So it all flows together very beautifully. So the reason why chemical bonds form is to lower the potential energy between the charged particles that compose atoms. So essentially when they're in close proximity, you've got all these positive charges and all these negative charges, and there's attractions there. It's kind of like, you know, in a movie where you're rooting for two characters to get together and you're just like, get together already. It's kind of the same deal with the atoms. It's like, just get together already and make a bond. So chemical bonds form when the potential energy, that's what E potential is, of bonding atoms, so upon making a bond, is less than the potential energy of the separate atoms. So they come together if it makes the energy lower. Basically, if they feel relaxed together. So you shouldn't date anybody who doesn't make you feel more relaxed than you feel warm. That's obviously what this means, okay? We need to learn life lessons from the atoms. All right, so the bond length then is going to be the distance between the atoms once they form a bond and once they are at their lowest potential energy. So it's the distance between atoms when the potential energy is minimized. It's funny, even though no one's here, I still talk with my hands all the time. I'm like, blah, 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 doing all my hand motions. All right. So there's two types of bonds that we're going to be really focused on, and probably you already know what they are because they're written right here and you've probably heard these words before. So we have ionic bonds and we have covalent bonds. They're two different types of bonding. So in ionic bonding, what happens is we take an electron and it gets transferred so it gets moved from one element to another. What elements are they? We've got a metal and a nonmetal. But obviously you already know this because we had to know whether something was ionic or covalent when we named it a while ago in chapter 3. So this should be familiar to you. We've got a metal and a nonmetal. Why do these bonds form? Well, we know that the metals from chapter 8 have a low ionization energy, meaning they lose electrons easily, whereas our nonmetals have a high electron affinity, so they gain electrons easily. And wow, those just complement each other so well, and the metals just transfer their electrons on over to the nonmetal. Then each essentially gains the noble gas configuration, and they're just little happy campers. Covalent bonds then form when electrons aren't transferred, they are shared. So electrons are shared between elements, and those elements, as you recall, I hope, from chapter 3, are going to be two nonmetals. So these are things that are going to be on the right side of the periodic table. Things that we use prefixes to name. So if you remember, it's easier to name covalent compounds, and what you'll see is that because that part was easier, it's going to be more challenging to write their Lewis structures. But also still really fun. All right. So why does this happen? Why are they shared? Well, we know that nonmetals have a high ionization energy, so they won't lose electrons. Right? It takes too much energy to lose those electrons. But if they can share the electron, then the potential energy will be lowered by sharing the electrons between the nuclei. And it'll be a relatively equivalent sharing. So we're going to have the most stability when you've got two positive nuclei equally sharing the electron in the middle. So this doesn't lower it a ton, this doesn't lower it a ton, but that in the middle really lowers the potential energy. We have one more bonding type, which is metallic bonding. And that's something that we really won't talk about a bunch because it really happens between metals. So this happens with metal to metal. And this is something that I studied in graduate school for my dissertation, but it's really not something we talk about here because the idea of having a lot of electrons in one place or a sea of electrons is probably more than we need to talk about for most of the molecules that we're thinking of. Okay, and so the reason why this is important is because it explains why metals are good conductors of heat and electricity, is because they've got a bunch of electrons floating around, kind of being spread out over all the metals. All right, so quick break, quick pause. My daughter has been sneaking in here whenever I have conversations with folks in the evening, and she brings in this little monkey. She calls this monkey Heartsy. And this is like the emotional support animal for all the students who see me in Collaborate Ultra late in the evening. And usually she only has one animal, which is her dog Taffy. It's a very loved dog. It used to be white at some point. It's had many surgeries to recover its nose and mouth. That's her support animal. She recently also discovered this. So like my house is a flow. This is her party puppy. These are some cats. But like literally every time she comes in, she makes me carry all of these animals at the same time. But now it's like comforting to carry these things. So basically what I'm saying is if you don't have a pet, maybe you just need an emotional support animal, stuffed animal, like my daughter thinks everybody should have. So yeah. And if you need to look at Heartsy to relax, she's a very cute monkey. She wants you to relax. So that's that story. Okay. So let's think about those valence electrons as dots, which I said is kind of the central idea in Lewis theory. So with the valence electrons as dots, what we're going to have to do also is represent the rest of the electrons in an element and the element itself somehow. So the element symbol, when we write it, is going to represent the nucleus, so all the protons and neutrons, as well as the core electrons, the ones that don't do any reacting. Then we're going to draw some dots, and these dots are going to represent valence electrons, as it says in the title of this slide. And they're going to surround the element symbol. So there's a couple rules for this. Essentially, you're going to place individual dots for each electron, and then you would kind of pair up the s electrons and then pair up the rest as well. All right, so let's start by thinking about how many valence electrons each element has. If you remember, these are the numbers at the top of the periodic table. So we've got 1, 2, 3, 4, 5, 6, 7, 8. We don't do a ton of Lewis structures with these elements in the middle, just because it's not very clear what's going on or how many valence electrons they have. So just don't worry about that. But let's just start with elements we're thinking of. So hydrogen plus its 1 electron. Then the next one we can do is helium. With helium, we're going to put 2 dots and we're going to pair them up because they're both in that s orbital. A lot of times students will say, well, does it matter which side we put them on? The answer is no. Who cares? Just put the right number of dots so that you know how many valence electrons you have and how they'll pair up. Then let's do lithium. So the core of lithium is helium, so we're not going to write those electrons. And lithium has 1 valence electron, so I'll put it here. Then beryllium has 2 valence electrons. Boron has 3, so I'll pair 2 of them like we have an s orbital, and then 1 by itself. Carbon would have 4 valence electrons. Nitrogen has 5. Oxygen has 6. And fluorine has 7. Wait, that's 5. What am I doing? Fluorine has 7, and neon has 8. All right. So you can do this with all the elements going down in the periodic table. Again, we're not going to be interested in the transition metals. So what Lewis theory tells us is that a chemical bond is the sharing or transfer of electrons to get or attain a stable electron configuration. And what do we mean by stable? Well, stable means that it looks like a noble gas configuration. So we want to match the nearest noble gas and have filled subshells. So again, just to remind you, with ionic bonds, the electrons are transferred. With covalent bonds, the electrons are shared. And you'll see how we're going to show that differently by how we show the Lewis structure. So the Lewis structure is what we draw to show how the bonds are formed. So the octet rule tells us that stable configurations have 8 electrons in the outermost shell. Right, so it's level. And 8 electrons means 8 dots. Just like you saw with neon up here, it had 8 dots, and so it is stable. There are exceptions to this rule for elements that can't have 8, which would be hydrogen and helium, because those can only have what's called a duet, or 2 electrons, as you saw up here for helium. They don't have any p, there's no p orbitals in the n equals 1 level, so they're just full with 2 electrons. All right, so let's start drawing some Lewis structures, or some Lewis symbols for ionic compounds. This is pretty straightforward. There's only 1 page of notes for this. The rest of this chapter is doing Lewis structures for covalent compounds. So you can see how they're quite a bit different from each other. All right, so when we're doing Lewis structures for ionic compounds, we have different ways that we show cations versus anions. So what happens with a cation, if you recall, cations are positive ions, and so they lose electrons. So the cation loses electrons. Wow. Sorry, I'm so bad at spacing out my words, and is written without dots. So if you remember, your metal is your cation. It's going to lose electrons, and so it's going to lose all of its valence electrons so that it will get the noble gas configuration. And so we're going to just write it only as the positive or positive ion. So the anion is the one that's going to gain the electron. Try to space this appropriately. It gains electrons. There we go. And is written with a full octet. So that means the 8 electrons. And how we're going to write it is within brackets to show that it's not like that on its own. And we have to show the negative charge to indicate that it picked up those electrons from somewhere to gain that octet. And the purpose of a Lewis structure for an ionic compound is that it shows the transfer of electrons. So let me show you an example. So potassium has 1 valence electron. So we're going to write the symbol for potassium with its little 1 valence electron. Now chlorine is a halogen. It has 7 valence electrons. So we're going to draw our little chlorine with 7 electrons around it. Some people also use X's instead of dots, so if you see that in any of the examples, don't be stressed. So what's going to happen? Well, we know that potassium is an alkali metal. It's going to lose that electron, and chlorine is going to gain an electron, so it has the same configuration as argon. So essentially what happens is, let me borrow my children's markers. The electron just pops right over there, and now it belongs to chlorine. And so to show the final structure, what we'll write is potassium with no electrons, just as the positive ion. Romy, are you? I don't know if you heard Tiny Romy's voice there. She came in looking for her stuffed animals, so I had to let her know that I had them all. She thought it was pretty cute that I showed it to you. Made her smile. Yeah, where was I? So the potassium ion is the positive ion, and then the chlorine now has an octet because it got an electron from its buddy potassium, and now it has the full octet in brackets with the charge. So +1 from potassium, -1 from chlorine. Overall, it's a neutral compound, and we showed that potassium lost its electron, that was valence, and now it belongs to chlorine. So what's cool about that is we can predict the formulas that things make by how many valence electrons one element needs and how, or to get an octet, and how many one needs to get rid of to have the noble gas configuration. This is the same thing that we've already been doing by using the charges and crossing them to make those predictions. This is just a more visual way to represent that. So we know that electrons are going to transfer until the metal has lost all its valence electrons, and the nonmetal has fulfilled the octet rule. So if one has given up all the electrons it has and the other still needs more, you can just adjust the number of atoms so that there are enough electrons to give the nonmetal metal an octet, and so the metal has lost all its electrons. Okay, so let's do a quick example where we're going to predict the formula of the compound formed when sodium and sulfur react. Again, this is something you've done already. So you know that sodium is in the first column, it's a +1. Sulfur is in this column, it's a -2. So you just swap those and we'd get Na2S, right? So you already know that because you know that sodium's a +1 ion, sulfur's a -2. You just swap them like we did when we were naming. That is straightforward. But let's do it a more visual way when we're thinking about the valence electrons. So sodium is a alkali metal. It's got 1 electron. Sulfur is under oxygen and it has 6 valence electrons. So let's draw those. 1, 2, 3, 4, 5, 6. Again, it doesn't matter how I write the 6 on which sides. It's just make sure it has 6. So sodium is going to give up its electron to give sulfur an octet. But look, sulfur now has 7 valence electrons. It needs 1 more. So we're going to bring in another sodium to transfer. So now what we have is 2 sodium ions. And we have sulfur, which now has an octet. And the charge is 2- because it picked up 1 extra electron from this sodium, 1 extra electron from that sodium. So now it has 2 extra electrons. So do you see how the formula is 2 sodium ions, 1 sulfide ion, just like we predicted from the charges. Now we're going to draw the Lewis structure. This should say of the compound formed between calcium and chlorine, but whatever. So calcium has 2 valence electrons. Chlorine has 7. So calcium's going to lose 1 electron. Now this chlorine has a full octet. But look, calcium still has that electron that it needs to get rid of to have the same configuration as the nearest noble gas. So what do? You bring in another chlorine atom with 7 valence electrons, and the other one goes to it. And so we have calcium 2+, and then we have 2 chloride ions, each one with an octet and a negative charge. So that's how the Lewis structure looks for something ionic. So before you start drawing a Lewis structure, you should always check whether it's ionic or covalent, because that will tell you the type of Lewis structure you need to draw. Almost all of the ones we're going to be drawing are covalent structures, but it's worth a check, because if we're drawing Lewis structures on the exam, which you will have a hard time with a question that has an ionic compound when you're trying to apply the covalent rules to it. Was that a hint? I don't know, most likely. All right, so that's pretty much all I can tell you about ionic compounds. There's not really a lot going on there. All you have to do is show how the electrons get transferred and show that they're both ions. There's a lot more rules when we're thinking about covalent bonds. All right, so with covalent bonds, what we're going to do is think about sharing electrons. So in Lewis theory, covalent bonding is depicted or shown as having neighboring or nearby atoms share valence electrons to complete their octets. Remember, that means 8 valence electrons. Or if we're hydrogen, we're only going to have a duet. No more than 2 for hydrogen. So when we're showing covalent bonding, the sharing, there's going to be some electrons that are not actually shared. They belong to a certain atom to complete the octet. So a bonding pair is talking about shared electrons. So they're shared by 2 elements, 2 atoms. And then we have what are called lone pair electrons. So these are not involved in bonding. They are only associated, or they belong to one atom to complete its octet. So let me start by showing you a Lewis structure for water, basically one of the most common compounds on Earth. So we've got oxygen, so example H2O. Oxygen has 6 valence electrons. Okay. Again, where I put the dots is arbitrary, so don't stress out about that. Then we've got hydrogen, each has 1 valence electron, and they're going to form a bond, and they're going to share those electrons. So now we've got hydrogen and oxygen sharing these electrons, and then we've got the electrons that still belong to oxygen. So I should have gotten my colored pens out before I started recording. So we've got these electrons here. These are shared. So these are bonding pairs. The ones in blue are bonding pairs. Then we've got the electrons that are on oxygen, these ones in pink. These are the lone pairs, and they belong only to oxygen. So a pair means two, so there's two sets of two. Two lone pairs, two bonding pairs. A lot of the time, just as a way to shorthand this a bit, we represent the bonding pairs. So bonding pairs are often represented by dashes. Okay, so instead of showing the Lewis structure of water where those electrons are shared like this, and you show the octet on hydrogen or oxygen and the duet on hydrogen, a lot of the time we just do a dash like this. And so it's more clear that these are lone pair electrons, right? And then the ones represented here, one dash represents two electrons being shared. Same thing right there. So there's still an octet, there's still a duet, it's just faster, basically, to write it with dashes instead of dots. So you might be thinking, well, is there ever a case where you have more than one dash between elements? And the answer is yes. So let's talk about how many electrons atoms can share. So in a single covalent bond, what we have is two atoms that share. That's not how you spell share, that's how you spell pair. Share one pair of electrons. So they are sharing a total of two electrons. Okay, one pair means two electrons. And an atom can make more than one single bond. It might only make one, it might make several, it depends on what that element needs. Let's look at chlorine, which is a diatomic gas, as an example. So chlorine has 7 valence electrons. And its friend, chlorine, also has 7 valence electrons. So if they were to get together and share these electrons that they have, then each of them would have 8. So if you look at it like this, you can clearly see that there are 8 electrons surrounding each chlorine. We've got one bonding pair in here. We've got 3 lone pairs on each chlorine, right? I'm using my pink to point out all the lone pairs. So 3 lone pair electrons, 3 lone pairs per, not 3 lone pair electrons, 3 pairs of electrons per chlorine atom. Same thing on this one, 3 more lone pairs, right? And then we've got our bonding pair. And you can see how it looks like each chlorine is surrounded by 8 electrons. The more common way you would see this is with the chlorines sharing the electrons as a dash, and so you can see that that more kind of looks like a bond. But again, still have an octet on each one. So then, if we move on to the next page, you can see that you can share more than one pair of electrons in a bond, and that's called double and triple bonding. Oi, I don't think I've hydrated in a while. We should all hydrate. So make sure you're doing that at home. I have no idea where I put my water bottle, but make sure you're staying hydrated. Okay, so with a double covalent bond, what we have is 2 atoms share 2 pairs of electrons to gain an octet. Okay? When we share 2 pairs of electrons, so now there's a total of 4 electrons being shared, so 4 electrons being shared. What happens is the electrons, or the atoms, are going to get closer to each other. So this is a shorter and stronger bond than a single bond. And also the electrons in the double bond count for both atoms to fulfill their octets. So a nice example of that is oxygen. So oxygen's another diatomic gas. We start with one oxygen atom that has 6 valence electrons and another oxygen atom that has 6 valence electrons. And now they're going to share this pair and also this pair. And so what that looks like, if we're just using the dots, is they're sharing all of these. Or if we're going to use the dashes, it looks like this. And that is the structure of oxygen. And you can see we've got an octet this way and we've got an octet this way. They count for both because they're shared. And again, these are the bonding electrons here. The ones in pink are the lone pairs on each oxygen. In a triple covalent bond, same kind of deal, but now 2 atoms share 3 pairs of electrons to gain an octet. So now we have 6 electrons being shared. And you can imagine sharing this many electrons. These bonds are even shorter and even stronger than the single or the double bonds. So on the next homework, I'll ask you to draw some Lewis structures, and based on what type of bonds they have, I could ask you what's shorter than the other, right? So the double bond would be shorter than what we have in a triple bond. So for example, nitrogen is one that we know has triple bonds. So let's draw the Lewis structure of nitrogen. It has 5 valence electrons with its friend nitrogen that has 5 valence electrons. Now they're going to share 3 pairs of electrons. 1, 2, and 3. The way I'm circling is also arbitrary. Like, it doesn't matter which ones I had circled or how I had written it. Just trying to show that now they're sharing 3 pairs of electrons, and I could show it with the dashes, or I could show it by sharing all of those electrons. So again, each one has an octet. The ones in the middle, in blue, these are our bonding electrons. And each nitrogen has 1 lone pair that belongs to just itself. Okay. So, how do we think about a model compared to a reality? How would we use Lewis theory to think about, okay, well, is an element really going to make a bond with another element? Or are these atoms going to come together? Or is this molecule that I'm predicting a real molecule, or is this just something that I invented and it really won't be stable? So what we can use Lewis theory for is to predict formulas of molecules and whether a combination of atoms is stable or not. Right? And so we know that water is stable. We know that because we use it all the time and it doesn't blow up in our faces. But how else do we know? It's based on Lewis theory. So oxygen has an octet. Each hydrogen has a duet. And so this should be stable. We've got octets, check, duets, check. There's no extra electrons that are floating around. What about the molecule H3O? Do we think that's something that exists? Well, let's try to make a Lewis structure. We'll put oxygen in the middle, hydrogens around it. We know oxygen has 6 valence electrons. It's using 3 of them, so it's going to have 3 left over. And you're looking at this and you're probably like, this is weird, because now oxygen has 9 electrons, and that's too many. That's beyond an octet. So more does not mean better. So this is no good. This thing is going to not be stable. But what if we took H3O and we made it a positive ion? So now we're taking 1 electron away. So now if we make this molecule and we show that it's an ion, now if we check our octet, yes, we have an octet, 2, 4, 6, 8 electrons being shared to oxygen. We have a bunch of duets where 2 electrons are being shared to hydrogen. So good. Now this thing is stable. Makes sense. The other thing that the Lewis model does is it counts for covalent bonds being what we call directional. I'll tell you what this means in a second. This is just a way of saying that they are shared evenly or relatively evenly between nuclei. This, what I showed you right here, the stability where the electron is in between those 2 nuclei and it's being shared, this is what a directional bond looks like. Okay? So, shared electrons are most stable between atoms. And each bond holds a pair of electrons. And that's what being directional means. Whereas with ionic bonding, we don't have directional bonds. We have non-directional bonds because there are what we call arrays of atoms, where you have just like a bunch of positive and negative charges in a sea of charge all being held together. You have a bunch of charge flying around. Sorry, my document camera got wonky. Let's launch that again. Apologies. While that's launching, my daughter wrote a song. Listen to this, it's so good. don't know why, but my audio cut off. Oh, that's sad. It was such a good song. Anyway, it launched again. I'll try to play it for you another time. It's so good. She made it up herself, and she played all the instruments except guitar. She played piano. She wrote the words. She weirdly came out of the bathroom and had the words for her song written out. Oh, she's so cute. Anyway, it's about being wrong sometimes. Anyway, so covalent bonding between the same two atoms means that you have really perfect equal sharing of electrons. They're equally strong, they're equally held, they're going to be shared perfectly equally. However, if you have two different nonmetals and you have a covalent bond, then that will result in what's called unequal sharing. Pretty self-explanatory, of electrons. So basically what we're saying is one of them is going to pull the electrons closer. So if you're thinking about a little cute tug of war between each atom, then one of them is going to be stronger and pull the electrons closer. So the one that's stronger is the one that has larger electron density near it. And this is going to be the one that has a higher electronegativity. And unequal sharing of electrons is known as bond polarity. So Lewis theory explains all of these different ideas. It explains that electrons are shared in a covalent bond. It explains that if they're two of the same element, they're shared perfectly. If it's two unlike elements, it's not shared perfectly. And it also helps us predict whether an element should exist, or I'm sorry, not an element, whether a molecule should form or not. So as we just mentioned, this idea of an atom being able to pull electrons closer to it is called electronegativity. So this is the ability of an atom to attract electrons in a chemical bond. And the trend for electronegativity, as you can kind of see from this graphic, is that it increases across a period or a row. So in each row, it increases going to the right for the most part. There's a few hiccups and exceptions. And it decreases down a family. So the larger the element is, or a column, the less its electronegativity will be. So fluorine is the most electronegative. As you can clearly see, cesium is the least electronegative. And if you want to remember, the order of the most electronegative elements is Funkel Bre. That's not bismuth, sorry. Bromine, iodine, Brish. So this is the most electronegative element, and it goes in decreasing order. So decreasing electronegativity. I'll just write En up here because I'll refer to it as oh, you can't see that. But these elements are still more electronegative than every other element on the periodic table. So these are the most electronegative elements, and you can remember it by this fun Funkel-Brish abbreviation. Okay, so carbon and sulfur and nitrogen and chlorine are fairly similar values, but it just helps with our little acronym. So Thonkel-Brish, if you remember, are the most electronegative elements on the periodic table in that order. And what that means is that when they're in a bond, they're going to pull electrons toward themselves. So let's look at some definitions down here. So differences in electronegativity tell us what kind of bond we're going to have, right? So if you have two of the same element and the electronegativity of chlorine is 3, right, then we basically have 3 minus 3, or here, I'll write it this way instead. 3 minus 3, the difference is 0, and so we call that a pure covalent bond. If we have hydrogen and chlorine, so chlorine has an electronegativity of 3, hydrogen has an electronegativity of 2.1, and we subtract that, we get 0.9. And so we call that a polar covalent bond. And basically the extreme of being polar covalent is that they're not even covalent anymore. So if we have NaCl, chlorine has an electronegativity of 3, and sodium has an electronegativity of 0.9. Their difference is 2.1, so that is an ionic bond. So we're not going to be really necessarily married to any of these numbers, or I'm not going to have you memorize them, but what I do want you to think about is that the larger the difference, the less covalent that bond is going to be, right? So the more polar it is. I think that's where we'll call it, and then in the next lecture we'll talk more about bond polarity and we'll start writing our covalent Lewis structures.